We're Team 27, working with Phoenix Children's Hospital, designing a novel shunt system for endovascular management of obstructive hydrocephalus. Our problem is hydrocephalus, which is the buildup of cerebrospinal fluid that enlarges the brain ventricles as seen on the image on the right. Some side effects of this include nausea, headaches, and vomiting in the patients because there's so much pressure on the brain. We're specifically focusing on obstructive hydrocephalus, which is the blockage between the ventricles, and the current solutions on the market are the VP shunt, the burr-hole shunt, and the ETV.
The global market value comes out to $474.01 million in 2004. Our CAGR is calculated to be 3.99% in the years 2024 through 2030 for hydrocephalus shunts. In North America, the largest market share for hydrocephalus shunts comes out to 37.9% in 2023.
So the key features of our device is we need it to be steerable in 3 dimensions. We need it to be delivered endovascularly. And so because of this, it'll drain to the internal jugular vein as opposed to the peritoneal cavity. And lastly, we want to use a supportive dilator for traversing the brain tissue. So all of these should serve to make it less invasive and reduce the recovery times. In order to accomplish this 3D steerability, we're using an inner deflectable catheter that allows for 180 degrees of motion. And this is going to interlock with an outer guide catheter, which is going to be able to rotate to account for another 180 degrees of motion.
Our shunt will be delivered through the venous sinuses, passing from the internal jugular vein to the sigmoid sinus and transverse sinus, where it will then puncture the sinus wall and pass through brain tissue into the occipital horn of the lateral ventricles. In order to pass through the brain tissue, the dura mater is punctured using a stylated needle. Then the guide wire will inchworm through the parenchyma, supported by the dilator, in order to prevent deviation from the path.
For our prototype, we modeled this inchworming technique using a brain parenchyma gel phantom made out of both gelatin and agar. We ran trials with just the guide wire only, and then also with the dilator for support. Using a target point, we aimed straight through the gel, and then measured the displacement from this target point on the exit side. As you can see in the image below, the guide wire and the dilator were closer to the target point than when the guide wire was just used alone. After recording our results, all our data was compiled into these violin plots, and as you can see from the graph, when the dilator was used with the guide wire for support, it was more consistent and had less variance in displacement from the target point. Here are our works cited, and thank you for listening.